Hey folks, Emily here. So in the first lecture in our series, you got a gentle primer on foundation models. You learned what they are, why they're interesting, and what you can do with them. In this lecture, we're gonna learn how to pick the right foundation model. So we're gonna understand what it means to evaluate a foundation model, and we'll learn some guiding criteria that we can use to just pick the right one, and then we'll close out with a hands-on walkthrough of running model evaluation benchmarks on AWS and especially with SageMaker. Let's get rolling. All right, so today, again, we're gonna cover the basics of foundation model selection. I get this question a lot, and it's actually pretty, once you learn just a couple of the guiding criterias, you're gonna be able to pick the right foundation model. It may seem overwhelming because you might think, oh my gosh, there's this massive universe of foundation models that are growing constantly and all these new flavors. And that's true, there are, that will continue to be true. But there's sort of this core foundation to picking the right foundation model. There's a core framework, mental framework that you can learn to help you be discerning in picking the right foundation model. It's a little bit like picking food at a buffet, if you will. Once you know what you're hungry for, and once you know what's healthy, it makes it a lot easier to pick food at a buffet. And so in any case, some of the considerations for you, different modalities across language and vision, different downstream tasks that you're interested in, the size of those foundation models, which then impact the accuracy of those, how easy it is to use a foundation model, licensing, previous examples, external benchmarks, etc. We'll kind of have this edgy question, which does it even matter to start with the right model? Because arguably, you just do everything in the prompting or you do everything in the fine-tuning, so TBD. So the basics of foundation model selection. So really, there are four dimensions, really. You've got the two edges of your x-axis here that I'm proposing, and then you've got two edges of your y-axis. So here in this horizontal line, basically you have two modalities that you're looking at. One is language, and then the other one is vision. Now, is the interplay between language and vision really a line, or is it more like a binary? It's unclear. You could say that, hey, it's just the one or the other. I'm just choosing the axis here because it's kind of cool. But so in any case, some models are language only. So the GPT version of models, BERT models, many language models, as you might imagine, are strictly language only. However, Vision has realized that LLMs are awesome and that language models are really demonstrating some interesting performance. And so the last 4 years have seen more and more vision models adopting some of the techniques and adopting some of the domains of these language models. And so CLIP is a image to text model. So CLIP is a model that you can use to upload an image and then get the text out of this. Originally, CLIP was just doing text classification, so using the captions of images to then classify those. There have been many open source versions of CLIP that have then been pushed into a number of different downstream tasks beyond just classification, but larger captioning, vision question answering, and some other applications. And then Stable Diffusion, of course, is another foundation model that is text to image. So Stable Diffusion, of course, lets you add a couple prompts, add some language as an input to your model, and then it will produce this novel model for you. And so when you're picking a foundation model, at a bare minimum, you want to know what the inputs and outputs of the models are. Does the model take language and produce language? Does it take an image? Does it take text? Does it output text, etc.? So once you know that basis about the domains, then that obviously limits down your scope to something a little bit more choosable. Then you have this second dimension here, which is generally small to large. So there's a huge variation in the size of foundation models. Some foundation models are quite minute. Like our trusty BERT model is just about 100 million parameters, which sounds like a big number, but it actually on disk is quite small, and it can fit on your GPU, on a single GPU or a single accelerator, really almost without fail. BERT is a very small model, especially BERT base is quite tiny. However, depending on the use case that you're interested in, BERT may be useful or may not be useful, especially if you're looking at open-ended language generation. Obviously, you're not going to go to BERT. You're going to go to a GPT or some other type of language generator. So as you move more and more into open-ended language generation, you're going to want a larger model. The model itself has more parameters in the neural network. The largest models have over 175 billion parameters. The human brain has more than 100 billion parameters. I forget exactly how many, but it's certainly more than 100 billion. It's a lot. And so language models are inspired by this, and then are increasing in size. And so these are these core, two core dimensions that you're caring about is the domain of the model and then the core size of the model. So once you have those four, there are a couple other modalities or considerations that we want to grapple with. And so to pick the right foundation model, again, the first tenet, the first step to consider is just the modality of this model. And again, as we learned, the modality of the model drives its output. So if I am a text-to-text model, or if I'm working with a text-to-text model, then I'll give it an input, which is, say, like, if I have 2 samosas and 1 samosa, how many vehicles do I have to sort of, again, throw at this red herring and see if it understands? And so a good LLM will tell me that having 2 samosas and 1 mimosa actually doesn't imply ownership of vehicles. It does, however, if it's a vehicle for entertainment, which I had some fun with. And so in any case, that's your good LLM. And then for my text to image, right, I'm going to give it an input, and maybe my input is a samosa sitting next to a mimosa on a table. And then I'll give it my negative prompts, which is, say, some curry for fun, and then some flowers. And so this is what I got. So Deep Floyd, which is another foundation model I was working with from Hugging Face. And essentially, so Deep Floyd's rendition of samosas with a mimosa, and then I added upscaling. And so here are these delicious samosas. They look pretty good. And then here's this rendition of a mimosa. I can tell you this doesn't look like any mimosa that I've had. And so I was curious about this. And for me, I was able to get better performance when I separated them out. With this particular model, Deep Floyd, it didn't seem to understand sort of novel concepts and putting them together. It was much happier when you took novel concepts and like kept them apart. So it's not common for mimosas to appear with samosas. It's common for them to appear separately. And so when I put them in 2 different prompts, it performed much better. And so now here is our samosas sitting next to a mango lassi, which, so this is still kind of getting the mango lassi, right? Because we have this, certainly this looks like a normal lassi, and then my mango flavor is down here. Obviously you would prefer them together. So there's some room for improvement. And so in any case, when we're picking the right foundation model, the first thing we'll do is start with the modality that we're interested in, and generally that's language or vision or some unknown wild card, right? You can use foundation models with really any digital modality, and my only word of caution here is that the quality of that model and the ease of execution of that model is really going to vary as a function of how widely adopted that model is. So language models and vision models are so good today because of years of really, really hard and dedicated R&D to make them awesome. And so for any other arbitrary modalities, definitely you can try it, but it might be hard unless and until it's been a little bit more widely adopted. And so, as again, we learned previously, you can recast your ML task as generative. So you can take your prompt, send your prompt to the model, and in traditional classification, it'll just add a label. In this new world of generative AI, we're actually recasting it as generative. And so this is a decision point for you in picking the right foundation model, is how deep down the generative AI rabbit hole do you want to go? And so in particular, you certainly can try any one of these tasks using a generative model, using an LLM. You can try doing classification with a generative model. You can try forecasting with a generative model. You can try recommendation. You can try anomaly detection, certainly translation, style transfer, visual search, arguably. And so it's interesting to explore these because you're using that foundation model. So you're still using that pre-trained base artifact that has multiple terabytes of images and text, possibly with lots of neural networks and trained on 1,000 plus accelerators. And so it's this really powerful thing. And so theoretically, you should be able to get some type of boost when you plug this foundation model into your other downstream task. However, you don't always need to. And what's interesting is that if you are sort of less on open-ended generation, and if you're more interested in doing just summarization or doing just style transfer, doing just classification, you can get away with a smaller model, actually. And so there's a benefit in trying to use a smaller model, as I'm saying here, because when you use a smaller model, obviously your costs go down, and your model inferencing runtime is also going to go down. Some benefits from using a foundation model, again, is just streamlining operations. Like when you have all of your pipelines, all of your data sets, all of your team resources and human brain power focused on making this one foundation model spectacular. In many cases, it's just more efficient. It's just easier to put everything into one really big project, which you then send into many different downstream applications versus having to like build and maintain and update like 40, 50, 100 different pipelines for all of these different models, which I know some of you do. I know it's really frustrating. And so when you run everything again in one model, it's just very efficient. It's just very streamlined. And so again, when you're using this foundation model, accuracy may actually just jump up as a boost. When you just use this modern pre-trained backend for your application, you may just see an uptick in performance. And it's fun because when you're using classification, you can still use all of these normal evaluation metrics. So you can use precision, you can use recall, you can use F1, etc. It's really fun to just run sort of the normal classification stack of eval just using these generative models. And so that's a big decision point, right? Is picking the right foundation model is how generative do you need your model to be? Do you want it to be writing multiple pages of really interesting text? Or do you want it to be just generating a sentence, generating a paragraph, doing summarization, doing extraction? There are a lot of different types of NLP use cases. And so if you're not interested in generic open-ended generation, but just using some of the boosts of your foundation model to solve a task, still use a decoder model, but you can get away with a much smaller and therefore less expensive and therefore faster language model, versus if you really want something that's going to help you write a novel or that will help you write a screenplay, then you probably want to use a larger language model because the quality of that text is just going to be higher. All right, and so we come to this other discussion point, which is the impact of size on foundation models. And so 2 dimensions here that we're interested in. One is the number of accelerators, or the number of GPUs. And so basically, again, foundation models take physical space. And because they take physical space, your accelerators actually, these things, these things have a physical, they're bound, right? There's a card that's sitting in here that can literally only hold so many bytes. Same with here, you've got 2 of them. And in this card, right, maybe I can fit a model with like 3 GB, right? So I've got 3 GB and 3 GB. So maybe I have 2 models that's sitting on this thing, 1 model here, 1 model there. And that's a smaller model. So that's 1 model that's parked on my single GPU. Alternatively, for a larger model, I might shard it across these 2 GPUs. So I might have a model that's maybe 10 GB on disk and maybe 6 billion parameters, and then I'm gonna run that on 2 GPUs. My larger model, on average, is going to be more accurate. Very, very well evidenced in the field and in the industry that larger models, on average, tend to be more accurate, but they also tend to be more expensive. So you see this core trade-off in the size of a foundation model, that as the number of accelerators or the number of GPUs goes up, accuracy goes up, right? So you're gonna see a more accurate model, that when that model generally needs more accelerators. You're also gonna see that cost go up because you're literally need to provision more GPUs, more accelerators, and the cost for all of that is gonna increase. You're also gonna see the inference runtime increase. So again, because you literally have to communicate with multiple GPUs, multiple accelerators, the inference runtime of that is just gonna go up. There's no way around it. Communication takes time. And humans are people, communication takes time. And so, yeah, so the inference cost is gonna go up. And then as a result of that, you have fewer deployment options. So you then become limited to only environments where you can provision and maintain all of those GPUs. Most commonly, obviously, on the cloud. Some people will try and do this on-prem, but most commonly on the cloud. And then on the flip side, when you're looking at smaller models, you get more deployment options, right? Because your model, when it fits only on a single GPU, then you can actually plug it into devices that already have a GPU. So I can run it on my laptop. Maybe I can run some super small ones on my phone. There are other, disconnected edge devices where I can take my model and park it. And so when you have a smaller model, obviously you have more deployment options, which makes it less expensive to run your model because you're physically paying for fewer devices to host it. So it's less expensive. The inference runtime is faster because it's communicating with fewer devices. The layers in the network are literally fewer, so it takes literally less time to just run a forward pass through the thing. And so, yeah, so it's less expensive, faster, and you have more options, but your accuracy may be lower. So there's this core trade-off here that you need to grapple with. There's no single answer for this today. You'll need to look at this, consider, in your business and your teams, what makes sense for you, and then come to some sort of core, set of model size, accuracy, performance, cost, runtime, and deployment options that you are all happy with and on board with. And so two ways to think about this. So the impact on size in foundation models is a fascinating debate. I love to just look at both sides of this debate. So let's poke at it. 86 billion, yeah. So the case for large foundation models. So why should we care about increasing large foundation models? And theoretically, why is this sort of more interesting? So the human brain itself has 86 billion neurons. And so theoretically, if we're trying to replicate human level performance, then we should see, there's some, 86 should be the number, right? That should be the target. Unless we're trying to replicate the performance of multiple humans, in which case, theoretically, maybe the number should go up. But that's just one data point. There are so many foundation models that are just breathtakingly large, right? That are just well north of 100 billion parameters, some cases hitting multiple hundreds of billions of parameters, Some of them are actually in the trillion phase. And so there's this, you know, wish, theoretical hope that, oh, well, maybe, you know, if we just scale it, maybe we get better performance. Also, logically, you would think that a larger data set should just have more information. Like, as long as I'm not just copying the same thing, logically, if I have, you know, multiple terabytes of rich, diverse, non-duplicated records, then there should be more information in my data set. So just logically, a larger data set should be better. And then as I have a larger data set, theoretically, I should also have a larger model. So in order to not overfit this thing and to actually capture all of the information that's in my data set, logically, I should also just have a larger model. And there's also this trend that like larger projects are just sort of inherently more inspiring. Like there's quite a few of us techies who are just more excited when you're running like a massive distributed system. And we just find that inherently more interesting. But you'll notice that that's not the top point, but it is a point. And then the case against large foundation models. So Stable Diffusion came in and was really fascinating because it was both really high performance, right? The quality of Stable Diffusion was great, and it was also single accelerator. So Stable Diffusion came out with a model that was, again, amazing, and runs extremely well on a single accelerator and a single GPU. And so that was sort of a shock, right? Because in LLMs, we'd been moving, you know, for a while, for years, you know, most of us thought like, oh, we'll just get larger and larger. And like there were some trends to decrease the size, but none of them were hitting state-of-the-art performance. And so Stable Diffusion was a big shock. So that was a really exciting moment. And then actually there were some updated scaling laws in 2022 that suggested actually increasing data sets much larger than previously, which meant we could use somewhat of a smaller model. So instead of maybe needing 175 billion, maybe we could get away with something that was smaller, but just trained on more data. And then there have been other models that outperform GPT-3 in many cases. So both the Alexa TM was a 20 billion model, parameter model, available on SageMaker through foundation models, same with Stable Diffusion. But in any case, the Alexa teacher model is better than GPT-3 in some use cases, right? So in some slice of the universe, the Alexa teacher model was actually outperforming GPT-3 on some downstream tasks. And then Instruct GPT came out and was shocking because Instruct GPT was 1.3 billion parameters. So this tiny model was then outperforming GPT-3 on their win rate with literally 1% of the parameter count. So maybe you really can get away with a tiny fraction of the parameter size. And then in Vision, certainly CNNs are still really strong. Like there's a lot of performance to be had just through convolutional neural networks. So CNNs are just great for vision. That's because they capture the visual structure. So like you've got your picture, and then your CNN starts in the top left, and it sort of learns the pixels in that top left, and then it moves across and it like convolves across the image, right? So it goes left to right, top to bottom, and it learns the structural relationship of the pixels and of the objects that the pixels describe, which is great, and transformers don't necessarily do that as well. So CNNs, and then encoders are still great. Obviously, having a lower cost makes projects more accessible, makes development more accessible, and then the lower carbon emission is always strictly preferred. And so this debate will continue to wage. I wholeheartedly expect the next couple years to continue to see, you know, edges in this, and I would say this space is your creative space to innovate. So as you are looking at interesting projects, interesting you know, ways to develop novel capabilities, think about this dialogue and think about sort of being inspired from both of these, and then try something new and show us all what's up. All right, and so to pick the right foundation model, we learned about modalities. We learned about language, vision, and this wild card. We learned about thinking about the model as being generative and sort of how deep down the generative, the open-ended language generation, how deep down that rabbit hole we want to go. And that should be, if yes, use decoder-based autoregressive models. And then these are sort of the categories that I tend to see for parameter counts. So you have some models that are solidly in the 1 billion parameters, like your GPT-2 in some of the different flavors. And so you can get some performance with the 1 billion parameter model. I'm not going to write a novel with it, but I might do some classification with that thing. Your 7 billion parameters is going to do a little bit more. You might need your 2 accelerators for your 7 billion, and it's going to do a little more. So maybe I'm not just classifying, maybe I'm like generating a headline or generating a summary. Your 11 billion parameter can answer some questions. It can answer questions that are quite obvious, that are well understood, that are non-ambiguous. Your 20 billion parameter model, especially if you do some instruction fine-tuning, you do some RLHF on that thing, you get some really high quality alignment data, you can have a conversation with a 20 billion parameter model. It should understand questions, and then you'll chain the questions, right? So you can use LangChain to just take the prompts and the answers, chain these things together, and then have like a rich dialogue with your model. So 20 billion is a nice spot because you still need maybe 4 GPUs, maybe 8 GPUs or accelerators, which is still a single box, a single instance. So you can run maybe one P4D, one P4DE instance on AWS, and park that in a 20 billion parameter model. Now that would be tight. I would probably try and get a couple instances and then maybe whittle it down from there. But at least you're in a feasible range. 50 billion is a lot. That's a large model. You're gonna need many more instances for that. I would probably expect you to be using 8, maybe 16 P4D instances, P4DEs, and you're going to be running some compilation to hit that with Trainium. But it's going to be very good, particularly when you train a 50 billion parameter model on an excellent data set. You will have a very good model at the end. It won't just be able to have a conversation with you. It can probably pass tests. You can fine-tune it and then again design it to handle very complex tasks. And then this last category is sort of north of 100 billion parameters. And this is like I'm passing the SATs, I'm writing novels, I'm translating these very complex languages, I'm doing very complex tasks. And so what I want you to see from this is that you can pick a model based on the task that you're interested in and based on the complexity of that task. So for the task that you have, if it's going to take human beings like an hour to think about this, translate it, write a good response, really grapple with the nuances of the question, 100 billion parameters, like you need a really big, really good model. But if your model is just like answering a really simple question or extracting a phrase or doing a really obvious translation, then you can pick a model that's smaller, which is going to be less expensive, easier, and faster at inference runtime. So those are some of your spectrums in foundation model size. And then again, the impact of accuracy on foundation models is always a thing. So we care about how good these models are. You want a model to be good. But it is not obvious to determine what good means. Good means different things to different people. I might say a good driver is someone who's safe. And you might say a good driver is like someone who's, you know, clocking F1 wins. So good means a lot of different things. And so we want to quantify that. And so in foundation models and machine learning, so accuracy is a common metric where you'll try to see, oh, how accurate is this model? Does it answer this correctly? Accuracy is actually a pretty misleading term, however. So it's more common to use precision, to use recall, to use F1. And that's because accuracy is dependent on how many samples you have. So if you're running the test out of 10 samples and you get 3 right out of 10, then your accuracy is only 30%, which sounds really bad. But maybe it picked like the most important 3, so your precision was really, really good, and that matters more in your use case. So all I'm saying here is think about it, like dive deep into it, and try and pick the right metric. You can use labeled data to evaluate your foundation models. So we talked about summarizing call transcripts, or generating content, updating content. All of these you can send to human beings to produce some labeled data for you. And it doesn't have to be massive. Like you can construct a labeled data set with like 30 samples, 50 samples, 100 samples. Maybe that takes you an hour. Maybe it takes you a couple hours with like 2 of your team members. So you can create what I'm saying is you can create a data set that is already labeled, and then you can use that labeled data set to evaluate your language model. So say you take your call transcripts from your call center and your customers are calling and they're like, oh, you know, hey, I loved this piece, but I didn't like that piece, and there's something wrong with my payment. What do I do? And then your call agent is talking to the customer and they're trying to get them back on track. And then after the call completes, your team members go like physically write a summary. They're like, yes, this is what happened, this is what we saw, and you get like a 5-sentence summary of the call. The next thing you can do is run a metric. So it's called Rouge. And the Rouge metric is a way to basically see how accurate the generated text is. So you take the text, send it to your LLM, get a response back, and see how like the ground truth the response from that LLM is. Again, so you can construct a labeled data set and then compute metrics to actually quantify how good your model is, how accurate your model is. Again, human feedback always wins. Like at the end of the day, when you have more responses from human beings, when you aggregate the responses from human beings using reward modeling plus some RLHF, that's always going to give you a better model at the end of the day. And in terms of picking the right foundation model as a base, again, I'm assuming you're going to evaluate this. You're going to pick the metrics that you care about. You're going to construct a data set that you care about. You're going to put the model in front of your users, your stakeholders, to see what they think, what they like. And then when you pick a higher quality model, it always means less work for you. So when you pick a higher quality model, it means you don't have to worry about the prompting as much. You don't have to worry about the prompt engineering as much, the prompt templates. Your fine-tuning doesn't have to be as aggressive. You don't have to be crazy about keeping it constantly up to date. It's just like generally a good model. And so that means you have to do less work because you're just starting with a higher model, higher quality model. And so that's how the impact of both accuracy and generally the evaluation of models can really impact your workflows. So when we're picking the right foundation model, again, we start with modalities across vision, language, and this wildcard. If it's generative, we use decoder-based autoregressive models. And then we have these different parameter sizes. We'll set our accuracy thresholds. And then there's this sort of continuum across open source and proprietary models. And so we've all seen that some language model providers are quite happy open sourcing their models, like Falcon is the most recent LLM that's at the top of the leaderboard that the TII has very graciously decided to open source. We're all very happy about that. And so using open source models frees you from relying on a vendor, right? That saves you from getting locked into a certain model vendor. And it lets you be a little bit more flexible with how you develop and how you maintain it. At the same time, when you pick a proprietary model, it means you're offloading some of that model development. It means you don't need to be as obsessed about the R&D, which, I mean, might impact you because I care about it, but not everyone does. But so in any case, when you pick a proprietary model, again, it gives you access to possibly more performant models more quickly. And so, yeah, so again, there's this vibrant and creative economy of foundation models out there in the universe today. And each of them have unique pros and cons. But most companies that I work with, most customers will have a really clear opinion about they only want to do open source or they only want to do proprietary models. If you don't have a clear opinion on that, then just run a cost-benefit analysis. Like look at the quality of different models. Based on the quality of the models, how well they work for you, how easily they integrate into your apps, then sort of make a decision about open source and proprietary for you. So again, this becomes our second sort of decision criteria. The most impactful pro tip I can give you is to find a working example. So there are tons of papers on archive.org. There's work published at top conferences. There's so many GitHub repositories. There's so many benchmarks on papers with code, online curriculum and coursework. Like spend time finding a working example. Like go spend the day or even just a couple hours looking for working examples that do whatever it is you are trying to do, and use that as your starting point. Because if it works already, then that mitigates so much of your risk because you're starting with a working example. And I would say just anecdotally, like a working example beats a concept any day. Like this is true for all of us. Like any day we come up with some crazy idea of something that we're trying to build out. It is always more powerful if you start that conversation with an example of it actually up and running, because that helps you win stakeholder buy-in early and often. All right, and so that leads us to the last part of picking the right foundation model, where we also want this working example to get started with. And then the last concept for you here is really find, use, and master external benchmarks. So obviously our friends at Hugging Face have an open LLM leaderboard, and then Stanford's Helm project from their foundation model research team is really awesome. They built this amazing taxonomy of ways to evaluate and consider the performance of language models, and created this great, robust repository for all of us to use. So both of those are really good. You want to get very comfortable at understanding these benchmarks, diving deep in them, spending time to learn about them, thinking about the different statistics, the different methods that they use, and understand what that means for your model. And then develop unit tests and edge cases for your domain. So not just the hella swags of the universe, but your healthcare life sciences, or your financial services, or your media and entertainment, your hospitality, like the problem that you are trying to solve right now. Start to develop your own edge cases for that, your own unit tests. Like build a prompt database for yourself of like, oh, in my use case, here's what I care about. I need to see summarization at this standard, or I need to see classification at this standard, translation at this standard. And then once you have your own sort of library of prompts, that becomes your source of truth. Then eventually that becomes much more powerful than the external benchmarks, because they don't have access to your data. They don't see what you're doing. And so that's like ultimately the best way that you can evaluate and then find the best foundation model. And then this last question is, well, what if a better model comes along tomorrow? Like, unambiguously, this will happen. You should anticipate that this will happen because it's too cool. The universe is too big to put everything in a single model. So plan to update your MLOps pipeline. Plan to refresh your training sets, your hosting sets, to ensure that you get the benefit and you expose yourself to getting your hands on a better model tomorrow, so that you can easily expose those benefits to your consumer. And with that, let's take a look at the demo. So in this notebook, we are going to evaluate a foundation model. In particular, we're going to look at Falcon. So this is Falcon 40B, and we are going to use labeled data. So we're going to bring a data set. This is actually the CNN Daily Mail from the Hugging Face data sets. And in particular, the data set contains a number of articles and then the highlights from those articles. And what we're going to do is compute what's called a Rouge metric, where Rouge is a statistic that tells us how similar two strings are. And so this is the Rouge 1, which basically a 1 means the two strings are perfectly identical, and a 0 means they have nothing in common. And so this metric will let us see how well our models are doing at summarizing this particular data set. And so the hope is that you can, of course, modify this to work with any summarization data set you're interested in to evaluate how well that model is performing at summarizing your data. And so just as before, you are welcome to use a short URL here, the bit.ly, to point to this notebook. So this time we're in the SageMaker Distributed Training Workshop repository, and this is number 10, LLM eval. And then the notebook here is Falcon 40B, and then this is the Rouge notebook. And you're welcome to go to the same link using the QR code depending on where you are. So let's check it out. All right, so just as before, we are in SageMaker Studio. And in the first notebook, actually, we created a Falcon 40B endpoint using SageMaker Jumpstart. So we'll do the same thing here. Excuse me. We'll do the same thing here. The endpoint has already been created, and we're going to point to that endpoint using actually Boto 3. So the notebook link points to a pre-created endpoint. It does have the code to create it, so if you'd like to use the notebook to create the endpoint and then invoke it in the same session, you're welcome to do that. You'll just use this predictor syntax. I wasn't in that scenario. I had a pre-existing endpoint and then just needed to point to it, so I ended up using Boto 3 for that. So this notebook uses Boto 3 as a result. So here we're using Boto 3, again, AWS Python SDK, and then this is pointing to not just SageMaker, but the SageMaker runtime, which is scoped to hosting. So all of the hosting APIs are then available through the runtime. And that doesn't mean sort of managing the endpoints, but it means just interacting with the endpoints directly. And then to basically invoke our endpoint, we're going to just pass the name of it. So here I'm just passing the name of the endpoint. And then again, if you're doing this in the same Jupyter session, you can just use the predictor.predict payload if you're using that handy model.deploy Jumpstart model. All right, so here is our payload. Same as last time, where we were passing in a variety of inputs to the model, and then so the inputs are the text, right, the language that we want the model to interact with, and then we're sending it other hyperparameters as well. And so the hyperparameters are, of course, ways to optimize and fine tune, so to speak, the output of the model. And so let's give this a shot. So we're sending in what is the purpose of life, and then Falcon instruct 40B says, as an AI language model, I don't have a personal belief system or a purpose in life. And so that's Falcon's response. And then same as last time, we have a variety of prompts. This one is sort of an open-ended question. Tell me about SageMaker, including a number of hyperparameters here. We invoke the endpoint, again, using Boto3, so client.invoke endpoint, and then we get this response back. And so the notebook continues with a number of others. I defined a little function here. It's just called query endpoints. And so this takes, as a default, handily your endpoint name. So actually I have this hard-coded here, but you can also just pass the variable that you created above. But in any case, this is nice because it serves as the default in that function. And then when you're invoking the function, you can just send the payload. And so the payload, remember, it's nice to have the payload be both the prompt and the hyperparameters, because then you can modify the parameters when you're modifying the prompt, and that's pretty useful to do. So you can write this to take the whole payload, and then this is just using that same function we saw. So we're invoking the endpoint, and we're dumping this payload into JSON, specifying that it's a content type application/JSON, and then we get this response, and then we're going to read it, decoding it in UTF-8, load that back into JSON, and then return it. And then we'll use this a couple times. So the payload here, building a website, can be done in 10 simple steps, which is then, of course, prompting the model to elaborate and to explain those 10 steps. And so we can look at this. And so here we go, the 10 steps. Choose our domain name and our hosting provider, and so on. And then, of course, the translation, sentiment analysis, question answering, recipe generation, summarization, and on we go. And so now we're coming to the new section. So first we're going to install some more packages, so transformers, datasets, evaluate, and so on. And then this ABSL-pi, which is useful for the Rouge metric. And then we'll load the datasets from Hugging Face, and then the datasets are rendered as follows. So 3 splits, so we have the train, validation, and test, and then each of these splits have an article. They have highlights from that article, and then, of course, the total number of rows, so about 287,000 articles in the training set, about 13,000 in the validation, and then 11 in the test. We're just going to use the training set here. The loop we're going to run through is quite small for the purposes of the notebook, but you're welcome to, of course, extend this as you're interested. So just to give you a couple examples of what the data set looks like, we're going to send in this article ID, so just the oneth, and then point to an article. And here we go. And so we have this, some article. It seems to be about Miami. And let's see if we can get a summary from this. So it's nice to have a character cutoff. This is to limit the likelihood that your endpoint is going to run out of memory. So when you're hosting the model yourself, you get to deal with the out of memory challenges. And so we'll use a character cutoff here of 2000. So this just grabs the first 2000 characters of the article and then tokenizes it to get closer to that 1024 token cutoff limit for the model. Actually, because the CNN dataset here is not, It doesn't seem to be like a formal summary linguistically. It's truly sort of articles. It's news articles, and then it's highlights from those that are useful in this context. So I found it helpful to modify the instructions. So instead of using the word summarize as the instruction, I just use the word highlights. And then I seem to get summaries that were much closer to the label data set. And so here we'll send this article to the endpoint. I am pretty sure you can eke out some performance gains just with modifying some of the hyperparameters. I'll leave that up to you, but I did find it helpful to have the max new token set to 66 just to keep the predictions shorter. So we have this empty rocket launcher. Goodness gracious. Did I do this correct? Oh, great. Okay, sorry, that must have been a previous one. Okay, let me make sure I'm defining this right. So article 1, yes, okay, we're in Miami. Now let's send this up one more time here. See if we can point to the right article. That must have been from a previous. Here we go, great. Okay, so this judge, and okay. Looks like it's certainly related to this one. And then the data set again is labeled, so it comes with a pre-written highlights of the article. And so this is the label for this article. And let's see if we can compute Rouge on this. So now we're going to use the Hugging Face Evaluate library, and we're going to load this Rouge score. Rouge is very sensitive to the lengths of the text, and it needs the two lengths to be identical, actually. So this little function just equalizes those two so that you have identical in length, basically predictions and labels. And so that's this function that just equalizes them. And then, so we'll use that function to then equalize the predictions and the label. And then we'll send those to this rouge.compute. And then we'll extract that. This gives you about 4 or 5 different metrics, and we'll pull out this Rouge 1 to see them equalize there and see what we get. So this is again equalized to 1, so that's about a 2% Rouge. Rouge is a tough metric to optimize for because again it's really focused on the strings being exactly the same when we know in real life that summaries can carry the same meaning but be phrased differently. So there's a bit of a challenge with the metric there, but nonetheless, let's proceed. So this little function for you should be a nice way to loop through your data set and compare the performance of the LLM with your ground truth in a summarization use case, so you can easily see how well the model is summarizing your data. So this is just a number of samples indicator you can change, and then you're going to loop through that. So we're going to go up to 10. And then as we go up to 10, we're going to point to the article, again, coming from that data set object set to the character cutoff. We're going to point to the label, just as we did before, which is the highlights for that article. And then we're going to send that to the LLM. So we're putting that into the payload here. So again, we're sending in the article, asking the LLM to define the highlights, changing some parameters here. The length of the highlights can change somewhat, so in a future version it might be helpful to modify this based on the length of the highlights. And then we'll query the endpoint. So we take this payload, send it to the endpoint, get our predictions, send both the predictions and the label to this equalizer. So they're equalized. Then we put them into the Rouge metrics, and then rouge.compute, and we'll get the results. From those, we'll extract that Rouge 1, and then this just writes those to a little text file here that tells you the article ID, the predictions, and then the Rouge metric. And so, of course, it's handy to write that to disk as soon as possible, because then you save the results. And so we can see those here. And so we have a number of articles going up to 9. And they do indeed have the highlights. And they also have the Rouge. And so in this notebook, again, we explored the Rouge metric in order to evaluate our foundation model and see how well it can perform summarization. So I hope you enjoyed it. In the next video, we're going to learn more about interacting with pre-trained foundation models. So that will include prompt engineering and then fine-tuning in particular. So I will see you there.